So, hello student, for the course of Foundation of Classical Electrodynamics. So, we are having class 4 today, lecture number 4, and in this particular module, mathematical preliminaries, we started the coordinate system last day. Today we will going to learn more about the coordinate system and then try to understand what is the meaning of orthogonal transformation. So, today we have class number 4. So, in the previous class, if you remember, we started the coordinate system and compare two coordinate system. One is Cartesian coordinate system and another is the cylindrical coordinate system, and try to understand that how the x, y, z and rho phi z, how they are related. So, today we will try to find out the relationship between the unit vector. Last day I mentioned that. So, unit vectors, because in the Cartesian coordinate system we have, say this is my Cartesian coordinate system, and in the same basis if I draw, so I am having a cylindrical coordinate system like this. So, this is x, y, z, and this system is basically rho phi z, where this is rho, this angle is phi, and if I move and say this, I am talking about this point. So, this is along this direction z. So, this is z as usual, but rho and phi is slightly defined in slightly different way. Now, the unit vector along this direction is the rho unit vector. The phi is this direction, the phi unit vector along the tangential direction, and along this direction I have z unit vector along this direction. So, the direction of the rho phi z is defined here. In a similar way, here we have in the Cartesian coordinate system, I have unit vector here, I have unit vector along this direction j, and I have the unit vector this direction, which is k. That is also well known and very easy to understand. Now, we will try to make the understand the relationship between the I, j, what is the k, and how it is related to the unit vector rho, phi and z. Suppose I want to define the I unit vector with the unit vector of rho phi z, how do I write this? So, you can see from the figure that now if I draw another figure, so just make a projection of this portion, and if I do the projection of this figure, it will look like this. So, then it will be easier to understand. In Cartesian coordinate system, this is along y and this is along x. So, I am making the projection of this part. So, this is my x, this is my y. I am now making a projection, and in that case I have the base like this. Rho, if you look carefully, is defined from here to here along this direction. It is rho is along this direction, this is a unit vector. Phi is calculated from x to rho, So, the phi should be from here to here, this is my phi, and the unit vector of the phi should be tangential to this point. So, this is my unit vector phi, and z is perpendicular to the plane. I should not bother about the j, because j, both the cases the z direction is same. So, now if I now, and along this direction is my I, you should appreciate this fact, along this direction is my I, and along this direction is my j. So, I need to just decompose everything, and then I can write the vector I in terms of rho phi and z. So, you can see that phi is here. So, I can replace this phi unit vector here to make it more convenient. So, my phi, I just replace it at this point, okay. And if this angle is phi, so this angle has to be phi, okay, because if you change this tangential point will going to change, and if it is 0, then this will be along this direction. So, that is why this angle phi and this phi, so, and this is phi unit vector. Now, if I decompose I along these two directions, so one I can write along this direction. So, what should be the value? It should be rho unit vector and the cos component of that, cos component of that. What should be the other direction? Other direction I can, so this is I, so another direction I can have here. You can see that rho and phi, they are perpendicular to each other. So, other direction I can decompose, and it should be simply the phi unit vector, because it is along the phi direction I am doing, and then sine of the angle. I am decomposing this I unit vector along this direction and this direction. Now, if this is phi, then the cos component will go along this direction, but the sine component go along this direction, which is opposite. That is why I need to put a minus sign here. Okay. What about the decomposition of the j component? This is straightforward. J is along this direction. I can decompose it along rho. So, if I do that, then it should be simply rho, and this angle is phi. So, that means it is sin phi, plus if I decompose along phi direction, it should be phi, and this component is simply cos phi. What is z? Both the cases z is same. So, I should not write it z, I should write it k. So, my k vector will be simply z unit vector. Okay. I should write like k vector, because if I write ijk, it automatically means these are the unit vectors. So, this is the way I can have ijk in terms of rho phi unit vector. Similarly, you can decompose this rho, which is even simpler, to ijk component in terms of ijk component. And if you do, then the rho unit vector, which is sitting here, can be decomposed here along x direction and y direction, and if I do, it should be simply I cos phi plus j sin phi. Similarly, phi unit vector, if I want to decompose along ij, phi is in this direction. So, phi is in this direction. So, now from this figure, if I want to decompose along j direction, it should be plus j cos phi, and if I decompose along this I direction, so it should be a negative sign and then I and sine of that component. Okay. What about the z? Z should be simply along k direction. So, here I decompose ijk in terms of rho phi z, here I decompose rho phi z in terms of ijk. So, I can have a relationship between these two and I can write this in a matrix form. That is interesting. This is a transformation. This is called the transformation of unit vectors. So, if I write this transformation in a matrix form, I simply write okay, I, j and k here. This side, if I write in matrix form, it should be simply cos phi minus sin phi and 0. Then I have sin phi and then cos phi again 0, and then I have 0 0 1 and I have rho unit vector, phi unit vector and z unit vector. This is the transformation from rho to I. If rho is and phi are given, then I can find out what is ijk. In the similar way, I can also have another transformation which is the opposite one, that rho phi z is equal to, if I make a transpose of these things, you will see if I simply make the transpose of these things, then I will get the matrix. These are the two transformation I am talking about, but the interesting thing is this matrix, whatever the matrix I formed. So, from the scratch we understand that how ijk and rho phi z are related, and I just decompose these vectors and find that okay, I, j, k can be decomposed in terms of rho phi z in this way, rho phi z can be decomposed in terms of ijk in this way, and then write a matrix form. But interestingly, there is a relationship between. So, if I know that this is ijk and this is rho phi z and they are related with the matrix M, this if I make a inverse of these things, then if I find the inverse of this matrix M, then rho phi z can be written in terms of ijk with this inverse matrix. But here we can see that these things are simply the transpose of that. That means the inverse and transpose are same matrix. So, that means there is a relationship between these transformations. So, these things we will going to learn next, and that is called the orthogonal transformation. So, these kind of transformations are orthogonal, and when we have a orthogonal transformation, this transformation matrix follows certain unique rule, and that thing we will going to understand quickly. So, what is orthogonal transformation? We have one basis and now we are going to another basis. The thing is that two bases are forming two different orthogonal system, and so the question is how I can manage to find this matrix which can go from one basis to another basis, and what is the what is the property of these matrix. Okay, so suppose in general I have a coordinate system having unit vector E1, E2 and E3, and another set I am having like E1 unit vector with prime, E2 with prime and E3 with prime. Okay. So, the way we have in the previous case, if I generalize, so E1 prime can be figured out from E1 set of this, but I need to have a matrix here. okay, this is J. So I can find out my E1 prime from the value of E1, E2, E3, that is why J is here with a matrix form here Ij, and you can see that J are twice here, that means we have a summation here. So basically I am having Ei, so these things are equivalent to, I am using this Einstein notation. So J is over summation, this value is 1, 2 and 3 if I am dealing with 3 coordinate. So I just removed the summation sign because I am using this Einstein notation. So it is simply Ei prime is Tij Ej. Now I find that both the coordinate here, for example, the Cartesian coordinate and this cylindrical coordinate, they are orthogonal to each other. I mean Ijk, they are forming a orthonormal basis, rho phi z also forming a orthonormal basis. So there both the coordinate system are forming orthonormal basis. So that means I can have an so I should write that E prime dot Ej prime, they are related with delta function because they are forming orthonormal basis. Okay. Not only that, the other transformation non-prime frame or non-prime, it is also delta Ij, that we know. Okay, so let us now, and now we know the relationship. So I just put this value here. So what is the value I am having? Ei and prime dot Ej prime, that is Ti say k Ek, because I am writing, and then dot T j say L E L, because this transformation I am using, whatever the transformation is written here. So prime with the non-prime, when I write in terms of this matrix Tij. The goal is to find out the properties of this T matrix. Well, I can now write I k T j L and E k dot E L this. Now this quantity is simply delta K L because they are forming again a orthonormal basis here. So that thing if I use, I simply have T I k T j L, these are two matrix element multiplied by this delta. So it will be 0 if k and L are different. So when k and L are same, then only I can have this. So I can simply write T I k and T j k. That thing, mind it, I start with this quantity. So that thing is already equivalent to delta Ij. Okay. Now you can we can, because these are the matrix element, I can manipulate that, and this manipulation is T this j k, if I make a transpose of that, then it should become T k j. So here I can write it in this way, T I k and this j k I just write T k j and then transpose of that. That will give you the value delta I j. Now this is a matrix element and this is a matrix element, k is sitting here. So I can write that simply T, matrix T, transpose of that thing, these are the transformation matrix, transpose of these things should be equal to unity. That means the matrix T for orthogonal transformation, these should be for orthogonal transformation. This is true. This has to happen. So, that means if you now look back to the matrix. So, here this matrix is eventually my T matrix, this matrix, and I am making a orthogonal transformation here. So, whatever the matrix I have here T transpose, and that should follow that T multiplied by T transpose is unity. So, in other way T transpose is equal to T inverse, that is the property it always hold, and you can check by yourself that the matrix we figure out, cos phi minus sin phi 0, sin phi cos phi 0, 0 0 1, you make a transpose of this matrix and then multiply with the original matrix whether you will going to get a unity or not, and you will going to get unity because this transformation is a orthogonal transformation. Well, I am not going to discuss in detail because that is not the case. It is just to make you understand that how from one coordinate system you can transfer to another coordinate system. So, let us continue with that. Now, we will try to understand how the vector is transforming from one coordinate system to another coordinate system, taking one coordinate system as usual Cartesian coordinate system and other is a cylindrical coordinate system. So, I am going to have vector transformation. Vector transformation. So, what should be the so vector transformation means what? So, that is the important thing. The same vector I mentioned earlier, the same vector A in Cartesian coordinate system I write A x I plus A y j plus A z k, right. The same vector I can write also in this cylindrical coordinate system, and then it should be A rho rho plus A phi phi plus A z z unit vector. Mind it, I am defining the same vector in two coordinate system. If this is my coordinate system, this is the vector I am talking about, A vector. If it is x, y, z, I can decompose it according to x, y, z components. But if I am using the these cylindrical coordinate systems, still it is possible to define this vector. So, this is my cylindrical coordinate system. In cylindrical coordinate system, the same vector I can define, but in that case the component will going to differ. Now, the question is, if I know the component, the point is, if I know the component of A rho, A phi, A z, can I get back the component A x, A y, A z or vice versa? So, that we are going to check. Suppose A rho, A phi, A z component is given to you. So, you know the vector, but A rho, A phi, A z components are there. Can I able to figure out what is my A x component, what is my A y component and what is my A z component, or vice versa? Like A x, A y, A z component is given to you and you are asked to find out what should be the component A rho, A phi, A z in Cartesian in cylindrical coordinate system. So, that I am going to figure out. Okay. So, let me write down the complete vector A. So, it is A x, and now I know what is the relationship between I with the rho phi z, because that I just figure out. right. I, what is the relationship between the rho phi z, I know. So, that I am going to use here. So, A x, and then I write rho unit vector cos phi. In place of I am just writing this phi, then sin phi plus A y. What was j? It was rho unit vector, then sin phi plus phi unit vector cos phi. And what is z? Z is simply z unit vector. That was okay. So, now I just simply write, take all the rho component 1, all the phi component, phi unit vector component in one bracket and z component in one bracket. If you do, I am going to get this. I just rearrange that A x, then cos phi plus A y, then sin phi, that should be with unit vector rho, plus minus of A x sin phi, and then plus of A y cos phi, that should be in under rho unit vector, and A z will be simply A z, z unit vector. Okay. Now, this vector is equivalent to whatever I am having is equivalent to A rho unit vector plus A phi unit vector plus A z unit vector. So, these two vector, whatever I have here, this one and this one are same, unit vectors are there. So, obviously, the component wise we are having the same value. So, I can now have a relationship with the component, and that is this. So, from here I can write my A rho is equal to A x cos phi plus A y sin phi. My A phi is this quantity, which is minus of A x sin phi plus A y cos phi, and finally my A z is equal to A z. So, these relationship I figure out, and from this relationship I can make everything in matrix form. So, A rho A phi A z is there. So, I can write it in this matrix form. Which is this. You can see that you are getting a same matrix that we figure out last time. So, this is a transformation matrix. So, if I want to find out, so if A x, A y, A z components are given, then you can find out A rho, A phi, A z component with this by using this expression. And in the similar way, if I can figure out these things, by making a transpose of this. So, I will going to get this, what is there, I have cos phi here, sin phi here, 0 here, minus of sin phi, cos phi and 0, and then 0 0 1, okay. And that here I just write a rho a phi is it. So, this is the way you can transform from one coordinate system to another coordinate system. Well, finally, I will introduce another coordinate system which is very important, and that is the spherical coordinate system. So, we now deal with the Cartesian coordinate system. So far we are dealing with Cartesian coordinate system and then the corresponding transformation, etc. So, now we will move to another very important coordinate system in electromagnetic theory. This is very important, and that is the spherical coordinate system. Let us define first, and then we will discuss about how the vector is defined, etc. So, spherical coordinate. In spherical coordinate, we define a point with r phi with the coordinate r theta and phi, r theta and phi. So, if I draw, so let me first draw carefully. This is x, this is y, and this is z, and I am having so along this direction is the rho. So, I should draw it here, and I am having a, so I am having a like this. Okay. So, now one by one define. So, a vector, a point here, make it red, P. How to define this point? So, I can have a line from here to here. So, this is the point, this is the value of say r. This r can be in any, I mean over this circle, any point, everything is r. So, I need to introduce another coordinate, and that is this, how this r is making an angle with x axis, like we had in this cylindrical coordinate system. So, this angle should be my phi, but it can be any point over this line. So, another coordinate I need to introduce here, and that coordinate here is theta. So, with these three coordinates you can define any point over space using this spherical coordinate system. Now, what should be the unit vector, because we are more interested with the unit vectors here. Along this direction it should be the unit vector r, fine. I have a a surface here. So, over the tangent along this direction, because theta is from here to here, it should be the unit vector theta. The direction of the theta is in this direction. So, unit vector, and phi will be here along this direction. This will be the phi, this is the tangential direction, and it will be the phi unit vector. So, these are the three unit vectors we have here in these points. Along this direction it is r, the tangential direction it is phi, and downward tangential direction it is theta. What are the restrictions? What are the restrictions? I should also mention the restrictions. So, the point P, so this is the point P. So, quickly I write. So, this point P is defined by r, then theta and phi. What are the what are the limits of this? So, r is less than alpha greater than equal to 0, theta is less than equal to pi and greater than equal to 0, and phi should be less than 2 pi and greater than equal to 0. So, these are the restrictions we have for r theta and phi. Well, what are the unit vectors? That is important. I also need to define the unit vectors. So, A is AR, then R unit vector. A vector can be defined in this way: theta unit vector and phi unit vector, and R dot R is theta dot theta equal to phi dot phi unit vector is equal to 1. R dot theta unit vector dot phi unit vector dot r unit vector, this is 0. That means they are forming orthonormal basis. Not only that, these are the right handed system. So, I can have r cross theta equal to phi, then theta cross phi equal to r, and phi cross r is equal to theta. So, they are forming right handed orthonormal basis. So, I do not have much time today. So, with this note I would like to conclude. In the next class we will discuss more about the spherical coordinate system, how the vectors can be transformed and how the unit vectors are transformed. I am not going to do the detailed calculation the way I did in here, and rather I like the students to do all this calculation by your own and try to find out you are getting the same result or not, and please take it as an exercise. But next class I will do everything. So, with this note I would like to conclude here. Thank you very much for your attention.